You see it every single day. But have you ever stopped to think about what's really happening inside a flame? Well, today we're diving deep into the science of a perfect burn. We're talking about the powerful chemical reaction at the heart of it all, combustion.
Seriously, think about it. Whether you're looking at a campfire or just the little blue flame on your gas stove, what is actually going on in there? It looks pretty simple, right? But it's actually this incredibly complex and fascinating dance of molecules. And understanding that dance is key to pretty much everything, from heating our homes to powering our industries. So, at its core, fire is this chemical reaction we call combustion. But it's so much more than just striking a match. It's a really precise process. Getting the balance just right, that's the difference between clean, efficient energy and a dirty, wasteful, and honestly, a pretty dangerous reaction.
Okay, so just like any good recipe, let's start with the basics, the essential ingredients. What do you actually need to make combustion happen? Turns out the list is surprisingly short, but it's the balance between them that changes everything.
You really only need two things. First up, you need a fuel. This can be anything, the natural gas in your furnace, the propane in your grill, or the coal in a power plant. And second, you need an oxidizer. Now, for just about every application here on Earth, that means oxygen, which conveniently we get for free from the air all around us.
So, once you have your ingredients, there are really only two ways things can go for your fuel. And it all comes down to one thing: how much oxygen is available. If you have plenty of oxygen, you get complete combustion. That's the clean burn that produces harmless carbon dioxide and water. But if you starve that reaction of oxygen, you get incomplete combustion. And that's when you create nasty stuff like poisonous carbon monoxide and wasteful soot.
You've seen this in your own house. Think about that steady, intense blue flame on your gas cooktop. That's the poster child for complete combustion. It's hot, it's efficient, and it's clean. But if you've ever seen an orange, sooty, flickering flame, that's a huge sign that the reaction is desperate for more air, and it's making all sorts of nasty byproducts.
Okay, so we know what a good burn looks like. But how do engineers measure it precisely? I mean, they can't just eyeball it. Well, they analyze the exhaust gases, and that means they have to account for absolutely everything, even the stuff you can't see, like water vapor.
So the first way to measure the exhaust is on what's called a wet basis. Think of this as the whole, unfiltered picture. It's the full composition of every single gas coming out of that reaction, including every last molecule of water vapor that was created. The whole shebang.
But here's the catch. A lot of the fancy gas analyzers engineers use, they can't even detect water. So to get around this, they use a standardized measurement called a dry basis. What they do is they mathematically remove all the water from the equation. This lets them accurately compare results from different systems, apples to apples.
Let's just look at a quick example to see why this matters so much. Imagine we have 100 moles of exhaust gas, and 15 of those moles are water. Okay, so on a wet basis, nitrogen is 60% of the total. But on a dry basis, we pretend that water doesn't exist, so our new total is just 85 moles. Now see what happens? That same 60 moles of nitrogen suddenly makes up over 70% of the dry gas. This is exactly why knowing if you're looking at a wet or a dry number is absolutely critical to getting the engineering right.
And all of this brings us to the central challenge for any combustion engineer: finding that perfect, just right Goldilocks zone for the air and fuel mixture. Not too little, not too much. You're always hunting for that perfect amount to get the job done cleanly and efficiently. Now, in a perfect world, we would use what's called theoretical air. This is the exact stoichiometric amount of oxygen that is chemically required to burn every single molecule of fuel with absolutely nothing left over. It's the ideal, the perfect target we're always aiming for.
But we don't live in a perfect world. It's pretty much impossible to get perfect mixing of fuel and air in a real furnace. So, to make sure every last bit of that expensive fuel finds an oxygen molecule to react with, engineers intentionally add a little extra, and we call this excess air.
Which leads to a pretty logical question, doesn't it? I mean, if adding a little bit of extra air is good because it makes sure you get a clean burn, why not just crank it up and pump in tons of extra air just to be absolutely certain? Well, it turns out there's a really big downside to doing that. This chart shows the trade-off perfectly. If you have too little air, what we call fuel-rich, you get that incomplete combustion we talked about. You're creating pollution and literally just wasting fuel. But if you have too much air, or fuel-lean, that's also a huge problem. You end up wasting a massive amount of energy just to heat up all that extra air that's not even doing anything. The whole game is to hit that optimal sweet spot right there in the middle. And that sweet spot, it's different for every fuel.
Something that burns really cleanly, like natural gas, only needs about 5 to 10% excess air. But a more complex, messier, solid fuel like coal, that needs a lot more, sometimes up to 60% extra air, just to make sure all of it actually gets burned.
All right, let's put it all together. How do engineers actually apply these principles to a real-world furnace? Come on, let's run the numbers on a quick scenario. Okay, here's our problem. We've got a furnace that's burning butane gas. We're feeding in 100 moles of fuel every hour and 5,000 moles of air. So the big question is, how much excess air are we running with here? Is this mix efficient or is it wasteful?
Now don't worry, the calculation is actually pretty straightforward. It's just 3 steps. First, we figure out the theoretical amount of oxygen we'd need for a perfect burn. Second, we calculate how much oxygen we're actually feeding into the system with that 5,000 moles of air. And finally, we just compare those two numbers to find the percentage of excess air.
And when you run the numbers, you get 61.5%. So this furnace is running with 61.5% more air than it theoretically needs to burn all the fuel.
Okay, so let's think about that number for a second. 61.5%. Is that good? Is that bad? What's the verdict? This right here is where the real engineering decisions start to happen. It's not just about getting a number. It's about understanding what that number means for how the system performs.
And the truth is, it depends entirely on the goal. If this was a coal furnace, 61.5% might be pretty good. But for a clean burning gas like butane, it's actually really inefficient. You're just wasting energy to heat up all that extra air. This is the constant balancing act for engineers, always tweaking that air-to-fuel ratio to find the perfect point between efficiency, cost, and environmental impact.
So the next time you see a flame, I hope you'll see a little more than just light and heat. I hope you'll see a finely tuned chemical reaction, a delicate dance between fuel and air where engineers are always, constantly striving for that perfect burn. Thanks for tuning in.